This is the original 2006 YouTube interface, featuring a low-resolution clip called The Avon Lady. In 2005, sharing a video meant dealing with tiny, pixelated files and long buffer times. Fast forward to today. The platform processes 500 hours of uploaded video every single minute and serves billions of views globally every day. This diagram shows a standard 3-tier monolithic architecture. A user makes a request, a single application server processes the logic, and a central relational database handles the storage. For most websites, this setup works perfectly. But watch what happens under modern media loads. If a creator uploads a 10 gigabyte 4K file, that transfer monopolizes the application server's bandwidth. Simultaneously, if 100,000 users try to watch a viral video, their read requests are blocked by the upload. Meanwhile, the database locks up entirely just trying to increment the view count for all those concurrent users. Software bottlenecks quickly translate into physical hardware failure. Compute resources max out, cooling systems fail, and the system burns out under the strain. Designing a platform at petabyte scale requires abandoning standard web development paradigms entirely. You have to replace the monolith with a series of highly decoupled, eventually consistent subsystems. If you try to upload a massive 100 gigabyte video file through a standard HTTP post request, a single dropped packet or transient network glitch forces the entire transfer to restart from zero. It is structurally unviable. The architectural mandate is strict. You must decouple the control plane, which handles metadata and authentication, from the data plane, which moves the actual raw video bytes. This chart shows initialization. The client talks only to the API gateway, authenticating and registering metadata. The gateway returns a pre-signed URL. Armed with that URL, the client slices the video into 5 megabyte chunks, transmitting them directly to a cloud bucket, completely bypassing application servers. This chunking allows for parallel, resumable uploads. If the connection drops, the client queries the server to see which parts arrived safely, and only retries the missing index. This design ensures that heavy data flows smoothly through specialized, frictionless channels, isolating transport failures to tiny fractions of the file. Once the object storage confirms all chunks have arrived safely, a synchronization barrier is passed. The system marks the upload as complete and fires an event into a Kafka message queue. That Kafka event triggers a massive fan-out process known as a directed acyclic graph, or DAG. The single raw video file is split and distributed across dozens of parallel worker nodes, each simultaneously extracting audio or encoding different video codecs. Because segments are processed independently, processing time is decoupled from video length. A 2-hour documentary transcodes almost as fast as a 10-minute vlog. The nodes then fan back in, reassembling segments into an encoding ladder, a tiered stack of resolutions enabling adaptive quality switching. By completely isolating the write path from the core application logic, the architecture prevents heavy network traffic from starving the compute resources required to serve the actual website. Curious, shifting gears, delivering the video is only half the equation. You also have to track engagement. How do you accurately count views for a viral video that is receiving millions of hits every hour? This chart illustrates the classic hotkey problem. If you update an integer in a database for every single view, you generate thousands of write requests crashing into a single row, enforcing a global lock that destroys write throughput. Forcing everything through one central point of synchronization inevitably causes the mechanism to jam, taking the entire platform offline. Under the constraints of the CAP theorem, you have to make a choice. To ensure the platform remains highly available during a massive traffic spike, you must sacrifice strong consistency. The mathematical solution relies on a conflict-free replicated data type, specifically a grow-only counter. This algorithm takes advantage of a strict constraint. View counts can only go up. Distributed servers can tally views locally without constantly coordinating. To implement this, the architecture diverts view events into 2 paths. The speed path pushes events into a Redis cluster, providing a rapidly ticking view count. The batch path routes events into offline jobs, filtering bot traffic to write an accurate total. The number you see ticking upward on a viral video is technically a distributed lie. It is an intentional, mathematical approximation required to protect the core transactional databases from collapsing. There is one final hurdle. Out of a catalog of nearly 1 billion options, the system has to determine exactly which video a specific user should watch next. It is computationally impossible to run a complex deep neural network against the entire video corpus in the 200 milliseconds before a page loads. You have to execute extreme data reduction, rapidly filtering an ocean of data down into a single, highly focused recommendation. The platform achieves this using a 2-stage information retrieval architecture: candidate generation, followed by deep ranking. This models candidate generation. The user's watch history and search queries are flattened into a single dense point called a watch vector. Using approximate nearest neighbor algorithms, an expanding radius instantly isolates the 200 video embeddings closest to the user. This first stage prioritizes high recall. It casts a wide net based on general relevance, narrowing the catalog from hundreds of millions down to a manageable few hundred before handing them off to deep ranking. Those 200 candidates are fed into a deep neural network, integrating hundreds of rich features to assign a precise score. Crucially, this ranking model uses weighted logistic regression to predict expected watch time, intentionally discarding click-through probability. If the system optimized purely for clicks, it would inevitably surface deceptive clickbait that viewers quickly abandon. Optimizing for total expected watch duration aligns the mathematical goals of the architecture directly with actual user satisfaction. When you step back from the isolated databases and machine learning models, you begin to see the platform as a single, living organism. This diagram reveals the complete global pipeline: the decoupled ingestion and transcoding networks, the Lambda architecture distributing massive write loads, and the 2-stage machine learning funnel delivering tailored recommendations, all bound together by edge networks and API gateways. It is a perfectly choreographed ecosystem where these disparate technologies synchronize flawlessly under an unimaginable weight of data. Building at petabyte scale is never achieved by finding a single software framework that can do everything. Ultimate system design is the art of anticipating unavoidable bottlenecks and orchestrating a symphony of highly specialized, loosely coupled subsystems to gracefully route around them.